How do computers solve large systems of linear equations? Imagine trying to solve a puzzle with thousands of pieces all connected. That's what large systems of linear equations can feel like for computers. But how do they manage to do it so quickly and accurately? Well, computers use special methods that break down these big puzzles into smaller, easier steps. First, let's understand what a system of linear equations is. It's a set of equations where each one is straight line, meaning each variable appears only to the first power and is multiplied by a number. For example, to equations like 2 times x plus 3 times y equals 5, and for times x minus y equals 1. When there are only a few equations, you can solve them by hand using substitution or elimination. But when there are thousands or even millions of equations, that's where computers really shine. One common way computers solve these big systems is called Gaussian elimination. Think of it as turning the puzzle into a simpler form called an upper triangular matrix. This means all the numbers below the diagonal are zero, making it easier to find the solution. Once in this form, the computer starts solving from the last equation and works backwards, a process known as back substitution. This method works well for small to medium systems, but can be slow for very large ones. To speed things up and make the process more stable, computers often use Lie decomposition. This method splits the original matrix into two parts, a lower triangular matrix and an upper triangular matrix. The system is then solved into steps. First, the computer solves the lower triangular system using forward substitution. Then, it solves the upper triangular system with back substitution. This approach is faster and more reliable, especially when solving multiple systems that share the same coefficients but have different constants. For the biggest and most complex systems, especially those with many zeros in the matrix, computers turn to iterative methods. Instead of solving everything at once, they start with an initial guess and then improve it step by step. The process continues until the solution is close enough to the real answer. Examples of these methods include the Jacobi method and others designed for sparse matrices, which are common in real-world problems like engineering and physics. Modern algorithms also look for patterns or symmetries in the matrix to speed up calculations even more. All these methods relying on basic math operations that computers handle with incredible speed and precision. They carefully manage rounding errors to make sure the answers are accurate. Thanks to these techniques, computers can solve huge systems of equations that are used in many fields like engineering, economics, and science. They turn what seems impossible for humans into manageable, solvable problems, making complex algebraic tasks approachable and efficient even at very large scales.